Okay, so the topic for today, now we're sort of getting deeper into computational complexity theory. And so today we will see, quite exciting, our first, I'll say, time complexity classes. The most important class, P, and maybe the second most important class, NP. Okay, so before we define what P and NP are, let me first give you another definition. I'll say let T of n be a function, from natural numbers. Natural numbers, and so usually whenever I say T of n, I mean T is running time, n is typically size of the input. And we'll say a language L is in D time T of n. So I'm defining what this complexity class is. This is a class of languages if there exists a Turing machine M and constant C such that M decides L and runs in T of n, C times T of n time. So in whatever we're doing, we'll assume that the machine always halts, right? So this is a machine that always halts. It runs in C times T of n time. This is our definition of D time T of n. Okay, this is where complexity classes start. Okay. Now let me qualify that by basically saying a standard Turing machine. And as we discussed, a standard Turing machine is one where the alphabet is binary. So the alphabet is binary and it only has one tape. Okay, now let me ask you a question. Define D time sigma of T of n using Turing machines over the alphabet sigma. Okay, so here's my question. Question is A, so what is the best, what is the best statement? And you'll see what I mean by best statement. What is the best statement? Can you say D time, and let's just say that the size of sigma is at least 2, so it's it's larger than binary. Can you say that this is a subset of this? Would you say the opposite? That D time T of n is a subset of D time T of n sigma T of n? Or can you say that they are equal? Okay, so actually there are 3 choices, and I even have the ability to poll. So let me go ahead and I will poll you. Yes? Yes, I have. Recording is progressing. Thanks. So I have put out a poll, so you can go ahead and answer. And so what is the best that you can say? Again, like if you think that they're equal, then of course that implies A and B, but then don't say A and B, then say C. Does the question make sense? Which of these is true? Think about simulation. Think simulation. And I should say, like, this is again, a standard one-tape Turing machine, just that the alphabet is sigma. Okay, so anyone want to justify their answer? Exactly. So it would be log sigma, right? Exactly. So you're exactly right. So the thing is, these are equal because a Turing machine over alphabet sigma can be simulated by a Turing machine over the binary alphabet, with log base 2 sigma overhead in running time. Right? So in some sense, this is sort of the obvious conclusion you can draw simply because the alphabet is larger than 2. So if you can do it with the binary alphabet, then the same machine can also basically exists over the large alphabet. It just uses 2 symbols. But you get this. And this is important. So this is nice because what it says is that this definition that I gave over here, this class, actually is independent of the alphabet, which is really useful. So it's good that this class is more general than just standard Turing machines, although it's defined with respect to standard Turing machines. So any questions about that? So if there's any confusion about this, please ask me. Okay, because there was there were people gave different answers. Do you understand? Does everyone see why this is the answer now? Okay. Now let me ask you another question. Okay, now think about this carefully. Now define d time k t of n using Turing machines with k tapes. And let's just say that k is going to be strictly greater than 1, so it has more than one tape. Now tell me what the best statement is. Again, we'll say a d time k of t of n. Remember, this is a class of languages. This is a set of languages. Is standard. B d time t of n is a subset of d time k of t of n. Or do we have C that these are equal? Okay, so I'll relaunch the poll with essentially the same choices. Okay, now tell me which is the right answer, and think carefully about what the correct answer is going to be. Okay? So this time, which most people who voted got that right, it's you can only make the obvious statement. You can obviously simulate a Turing machine with a single tape using more than one tape. So this is the obvious statement. Equality is not necessarily true because we did not show that you can simulate a k-tape Turing machine with a constant overhead in time. Now recall that what we proved, that a k-tape TM running in t of n time can be simulated in, I'll just say, O of k t of n squared time by a standard TM. And Henny and Stearns prove that actually you can get better. You can get O of n t of n log t of n. So what this tells us, if we use Henny and Stearns, we know that d time k of t of n is contained in d time t of n log t of n, but not in t of n. That we don't know. And again, I'm absorbing the k and the constant because k is a constant with respect to this class. So we have this containment. Yes, the efficient simulation thing. I'm sorry, the efficient simulation. But even if we didn't do efficient simulation, then we definitely know, like using our, I guess, inefficient efficient simulation theorem, we can prove that. This is what we did prove, right? There's a stronger statement, but we proved this. Now, the reason that I want to show you this statement is that it is possible that more tapes gives more power, but not by a lot. At most by a polynomial factor. In this case, it's even just a log factor. And so now let me define the class P. And so P is the union over all natural numbers C of d time n to the c. Okay? And what is important to note is that P does not depend on the number of tapes or the alphabet size. Indeed, any reasonable Turing machine model that you come up with typically has some kind of an efficient simulation theorem, efficient up to some polynomial, and therefore P does not depend on the number of tapes or the alphabet size. Or I'm just going to stick my neck out and say it just doesn't depend on the specifics of the Turing machine. So even if you used a RAM model, with a RAM model you can get a quadratic speed up, but then that is then subsumed by the fact that you're taking the union over all polynomials. Any questions about what the definition of P is? For additive constants, meaning I mean, in some sense, I mean, you could fold the n naught into the constant c, into this constant c. right? You can fold any sort of initial n naught using this. So this is effectively asymptotic, right? Because this is an upper bound, yeah. So any questions? By the way, I mean, you could maybe, I could also have said maybe O of t of n time if that was preferable. I'm a little careful about like putting O's because when you start multiplying things, you have to be a little careful that you're maintaining asymptotics. But yeah. Okay, so P does not depend on the tape, so the alphabet size, and so this leads us to a statement. Again, this is not a theorem, this is a hypothesis, and this is called the strong Church-Turing thesis. The strong Church-Turing thesis says that every physically realizable model of computation can be simulated by standard TMs with polynomial overhead. This is a statement, again, which has stood the test of time, and I will discuss this later on, but there are claims that quantum computers might actually violate the strong Church-Turing thesis, and I'll discuss this later when I talk about the factoring problem. But again, for any other model that has been developed, it has basically validated the strong Church-Turing thesis. Now, the importance of the strong Church-Turing thesis is it says that P does not even depend on the model of computation, as long as your model of computation is physically realizable. So this is sort of saying that P is the class. P is like an efficient class regardless of which specific computational model you choose. Now, we can't prove that because we cannot possibly know what computational models exist. But the strong Church-Turing thesis says that if you have a physically realizable model and you can simulate it, of course, by standard Turing machines with polynomial overhead, then you get P again. Any questions about that? This is more of a philosophical point. And there are some philosophers who will ask, our brains, do they violate the strong Church-Turing thesis? And there are things like that. And this took a lot of this was developed in the 50s, 60s, and 70s. I'll sort of make a few points over. So P contains all languages that can be efficiently decided, and this is also known as Cobham's thesis. And I think this was also this was in 62. The nice thing about P is P contains the closure of efficient algorithms, meaning that an algorithm that invokes a polytime algorithm polynomially many times is also polynomial. Right? I mean, you might think that, linear time is what is really efficient. But the problem is if you have a linear time procedure that calls another linear time procedure, then you get something that is potentially quadratic, which is not linear anymore. So then you don't have closure. You don't have this sort of sense where an efficient algorithm that calls an efficient algorithm is also efficient, totally, when you put everything together. Right? So the thing is, even if you add subroutines, you still get something in P. So P contains a closure. This is a nice property of P, which allows for mathematical study. But maybe, in some sense, these are more, let's say, philosophical discussions of why P is interesting, and a more, yeah, yes, yes. Mm-hmm. Yeah, so maybe the way to, this has been poorly worded on my part. I'm just saying that I'm just saying that P, I'm defining efficiency with respect to P, which is what you're saying. And I'm just saying that this is explicitly stated by Cobham for the first time. I think that this is probably the place where and I'll show you, there are actually multiple independent instances of people coming up with essentially this notion, but I think Cobham was maybe the first to maybe write it closest to this language. But I don't even think that the notion, I don't know if he was the first one to use P. But I think at that point there was this discussion of, there was computability theory, which is talking about what is computable. And then there were a few researchers who were talking about what does it mean to efficiently compute something, and then they sort of converged upon the definition of P. And I think sort of the most important, and this was said by Edmonds in '64. Interestingly, Gödel had said the same thing in a lost letter, which was rediscovered not too long ago. He had a letter in the 50s where he was basically talking about P, but it was actually, he was talking about the P versus NP problem. And this is the earliest reference, and the letter was lost, and then it was actually discovered maybe 3 decades ago. And on the sort of the other side of the Iron Curtain, Trachenbrot in the 50s was also discussing the same notion, and then there is Cobham in '62. So this is just sort of a laundry list of various people who are discussing it. And what they discovered is that for many languages or problems, existence in P implied a non-trivial algorithm that beat brute force. And we'll see more of this as we in this course over the next few lectures. But I think this is really where it sort of cemented this notion that P is interesting, because mathematically, when you discovered that a problem was in P, for a large class of problems, this usually implied an algorithm that beat some brute force solution. And this came up a lot in sort of optimization theory, and this is where Trachenbrot started. Okay, so much for maybe a more philosophical discussion of P. And now let's go more into a mathematical discussion. And so now that we've defined P, let's define the class NP. I'm going to use a definition which is maybe different from the one that you may have seen. So I'm defining what NP is. And I'll say L is an NP if L is polytime verifiable. Okay, and let me define what this means. What I mean is there exists polynomials P and Q such that, okay, there exist two polynomials such that for all x in the language such that x has length n. Okay, so take any instance in the language, there exists a certificate. There exists a certificate y, and the length of y is at most this polynomial. There exists a certificate. Okay, so I should actually say that maybe before, let me sort of put it over here. There exists a polynomial P and Q and a Turing machine M such that, okay, so there exist two polynomials P and Q and a Turing machine M such that for any x that's in the language, there exists a certificate y which is at most of polynomial size. No, okay. Such that, okay, so sort of M x comma y accepts in Q of n time, and for all x not in the language, for all certificates y where y is of at most polynomial size, M of xy rejects, again in Q of n time. There's a bit of a there's a bit to parse. So maybe I haven't written it in the best way. I could just say there exist polynomials P and Q. So Q is the running time of M. P is the certificate size. So a language is an NP if it's not clear that you can decide whether X is an L, but you can get a certificate that X is an L, and checking the certificate can be done in polynomial time. So I want to give a different picture. This is like, this is also referred to as, a prover verifier system. So let's say here is this entity which needs to verify. So let's just call this the verifier. And the verifier wants to determine, so it's given X, and the verifier wants to know, is X an L? Now the verifier is unable to do it. So the verifier is going to get some help. It's going to get something called a certificate. It's going to get a certificate, and then based on both the input and the certificate, it's either going to say yes or it's going to say no. So the verifier gets the input and the certificate. Now the guarantee is if X is in the language, there is a certificate, there is a certificate making, so I'll just call this M. This is the Turing machine M, which I call the verifier, making M accept. If X is not in L, then M will never accept. No matter what the certificate is, M will not accept. Again, and the certificate is always of polynomial size. So this is the definition that I'm going to give of NP. The typical definition given is using non-deterministic polynomial time, which we will talk about shortly. But I want you to understand this definition because I think this really captures the essence of NP in a way that non-determinism doesn't do as cleanly. The essence of NP is that it is verifiable in polynomial time. P is decidable in polynomial time. So let me pause here and take any questions that you have about this definition. So let us now consider a few examples of languages. And let's start from something to do with graphs, just to make it more concrete so that you can visualize. So in a simple graph, so by simple I mean there are, it's no parallel edges, simple undirected graph, right? So you've got vertices and you've got edges between them. A clique is a set of vertices. Clique C is a set of vertices such that for all uv in the clique, uv is an edge, right? This is also called a complete subgraph. So a clique means if this is a clique, then you have all possible edges amongst this. So let the language be all graphs. So that G has a clique of size at least V over 2, clique of at least half the vertices. This language. So this language is obvious, you can see that it's in NP. Why? What is the certificate? So what is the certificate for any graph that's in this language? What would the certificate be? It would be the clique of that size. The certificate is the clique of size at least V over 2. Now what does the verifier do? Let's look at what the verifier does. Verifier takes G and a certificate. Now what is a certificate? Certificate is a potential clique. It's a potential clique of size V over 2. So the potential clique, one could just think of as this is the same thing as saying this is a subset of vertices of size at least V over 2. And I'll call this C. The verifier checks if all edges in C are present. So we'll just say step 1. I should call this step 0 because this is sort of like the input. Checks if all edges in C are present. And if yes, accept, else reject. Okay, so this is the verifier. Now think about this. If the graph is in the language, there is a certificate that will make the verifier accept. What is the certificate? It's the clique. Suppose the graph is not in the language. Then there is no way the verifier will accept, because no matter what subset is provided of size at least n over 2, v over 2, it will discover that there is some edge that is not present and it will reject. So you cannot fool this verifier into accepting a graph that is not in the language. Any questions about that? Right, so no matter what certificate is provided, or no matter what set is provided, the verifier can check whether it's a valid certificate or not. Let's consider another language. So L is, I'm going to say, it's going to be a bipartite graph. I'm sorry, G is equal to V1, V2, E bipartite. So it's a bipartite graph such that G has a perfect matching. Now, what does perfect matching mean? It just means that here's V1 and here's V2. A perfect matching is a set of vertex disjoint edges that's incident to every vertex, right? So this is a perfect matching. Is this language in NP? Is this language in NP? Okay, but you're thinking ahead. Okay, so but if it's a two-sat problem, why would it not be an NP? But that doesn't mean that it's not an NP. The question is this an NP? Sure. That the fact that it okay. So yes, it's true that L is in P, but that's a fairly non-trivial result. You have to use like max flow min cut, or I mean you can model it as a max flow problem. Not through 2SAT. But you should be able to see that it's an NP quite easily because the certificate is the matching. It's easy to check if a potential matching is a matching or a perfect matching. It's easy to check if a potential matching is a perfect matching. Right? So L is an NP. Does this help? Is this giving you a better sense of what it means to be an NP? Lots of graph problems are sort of almost, if you just look at the definition will tell you that it's an NP. It's actually, the languages are literally stated as the existence of a certificate, which is easy to verify. By easy, I mean in polynomial time. Okay? Mm-hmm. So think of it as you get to choose what the certificate is supposed to mean. So you don't need to worry about the certificate meaning something else because then you could just reject. So you're trying to design the verifier. So you are imposing what the certificate means. So think of this as a game between you and an adversary. Right? You're trying to design the verifier and you're going to tell the adversary, you need to provide me a certificate that means blah. So in this case, the certificate should be a subset. If you parse the certificate and it doesn't give you a subset of this size, then you just reject. If you parse this certificate and it's not a set of edges, you just reject. Because in the end, everything is encoded as binary, right? So your verifier is going to parse the certificate and interpret it as a set of vertices or a set of edges. So if you get a bad certificate, you just go ahead and reject because the only thing you need to show is that there exists a good certificate, not that all certificates are good. Does that help? So the thing is, if you got a certificate that meant something else, it's fine. There could be multiple different interpretations of certificates. You get to choose, you as in you being the verifier. The verifier gets to choose what the certificate is supposed to mean. I guess what you're getting caught up is like in the semantic, like what is the semantic meaning of the certificate? Mm-hmm. Mm-hmm. Right. So you'll see that typically for most languages in NP, the certificate is not hard to guess. You can come up with like crazy languages where maybe one has to think, and indeed actually we will later on discuss that for certain languages it's actually not obvious what the certificate is going to be, yet it turns out that they're in NP. Yes, exactly. But now let me give you some more problems where now one has to think a little bit. Okay, let me ask you another question now. Hilbert's 10th problem. Hilbert's 10th problem was given a set S of Diophantine equations. So Diophantine equations are equations where all the coefficients are integers. Right? Like x squared plus y squared equals z squared. X cubed plus y cubed equals z cubed. X cubed minus y squared equals 1. Like equations where all the coefficients are integers. Given a set of Diophantine equations, does there exist an integer solution? This is the question. Does there exist an integer solution? So you get a set of Diophantine equations and you have to determine, is there an integer solution? Is this language in NP? Right? Or one can actually write the language. It's sort of I put the encodings of S. S has an integer solution. Is L in NP? So, yeah, let's take a minute. Does anyone have any questions about the question? Like, do you understand what the question is asking first? Right, it's a polynomial equation where all the coefficients of integers and the powers are also like positive integers. Yeah. Does there exist an integer solution? So like if you have, for example, x squared plus y squared equals z squared, does this have an integer solution? Yes. 3, 4, 5. Pythagoras, right? What about this one? Not so obvious, but it turns out there is. I'll give you one. 1, 7, and 5. 1 square plus 7 square is 50, which is 2 times 25. This has a solution. X cubed plus y cubed equals z cubed. The answer is no. This is Fermat's last theorem, or it's a special case of Fermat's last theorem. right? And so what Hilbert asked was there an okay, so we'll get to Hilbert's question, but you could say this is a language now. This is in the language, this is in the language, this is not in the language, because you can just take the binary encoding of such a statement. Right? One can come up with any Diophantine equation. So does there exist an integer solution? So someone had a comment. Yeah. So yes or no? Do you think this is an NP? Is this an NP? Okay. That's right. That's exactly right. So the integers, given integers, you can check, but so there is a certificate, but the certificate might not have polynomial size. Right? So there's an obvious certificate, the solution, but it might not have polynomial size. Mm-hmm. Yes. Indeed, you could say, okay, but can we prove that the certificates have polynomial size? Actually, the answer is no. Hilbert's 10th problem was proven to be undecidable in like a monumental work by Robinson and Matyasevich. So actually, we know that the certificate, you actually cannot bound the size of the integers. So it turns out like this problem, it's actually undecidable. You can reduce the halting problem to a set of Diophantine equations. Okay, but good. There was a point raised earlier. Let me now ask another question. So let me suppose set of linear equations. Set of linear equations. So given AX equal to B, does there exist a solution? So think of if you want to make it concrete, A and X, the entries are all integers. But I'm not asking for an integer solution. I'm just saying, does there exist a solution of this linear system? I'm sorry, in the previous one? The certificate would be the integer solution. The certificate would just be the integers that satisfy this equation. So for example, for this, the certificate is 3, 4, 5. For this, the certificate is x equals 1, y equals 7, z equals 5. For this, there exists no certificate. So it satisfies sort of the NP type conditions that whenever it's in the language, there should be a certificate. When it's not in the language, there is no certificate. On the other hand, the problem is a certificate might not have polynomial size. And that's why this language is actually not in NP. It's been proven that it's actually not in NP. It's been proven that this is undecidable, so it's way beyond NP. But does that make sense? So the certificate is the solution. Okay, so now let's look at this setting. A set of linear equations. Does there exist a solution of this linear system? Is this an NP? Good. So you're thinking along the right track. So it seems like there is an obvious certificate. Right? The solution. The solution is the certificate. And so this goes back to the comment that, if you could bound the size of the certificate, then it's seemingly you can do it. And indeed, for a set of linear system, you can, because if you actually apply something called Kremer's rule for solving linear systems, when you apply Kremer's rule, for any solution, and remember this, x is like, it's going to be some vector, right? This is like r to the d. These are matrices, right? Ax equal to b is a linear system. For any solution x, the entries can be represented as ratios of determinants. And indeed, if you look at what this is, you can actually say that you can say that the bit complexity of x is polynomial in the bit complexities of the entries of A and B. This is a non-trivial statement, right? But the thing is, if you look into the theory of solving linear systems, you'll see this thing called Kremer's rule is one way of writing out the solution. And for any solution, the entries can be represented as ratios of determinants. And if you look into it, the bit complexity of anything in the solution is polynomial. By the bit complexity, I mean like the number of bits you need to represent any entry in A or B. Does this make sense? And so you can actually argue that if there is a certificate, that if there is a solution, that solution has polynomial size. And therefore, this is an NP. Indeed, it's not just an NP. This is in P. Solving a bunch of linear systems. You can do Gaussian elimination. Right? So this problem is actually in P, but this is an NP. Just to give you the argument that this is an NP. This is also in P using Gaussian elimination. It's also in P, but okay, so that's a good point. You're right that you could make it large, but then when you say they're close to each other, you would have to use more and more bits of precision to make them close but not parallel. And therefore, that will get reflected in the solution. Right, so and exactly. So even in the division step, what you get is you only need to go up to a polynomial number of bits. You'll always have a polynomial bit representation. Like if you represent everything basically as ratios, right? As opposed to, instead of representing a decimal, represent everything as a rational number. And you'll see that all of it basically boils down into sort of additions and multiplications of entries. And you'll only do polynomially many. Right, so and also, this might not be a square matrix. So in that case, but you're right that you can use Kremer's rule and you'll usually get, you can represent, okay, so maybe I should have, I'm sorry, so I kind of fudged this. I'm saying that Kremer's rule applies, when this is a square. If this is a square matrix, you apply Kremer's rule. But in general, you can do this. So I should have maybe written this over here for square matrices A, but in general, And to see this, this is Gaussian elimination. Now I give you I gave the examples on this page exactly to address situations where the certificate is not obvious. So it's not that obvious to show that something is an NP. So let me give another example. And this is going to require you to think a little bit. So I'll go again with G. We'll talk about cliques again. I'll say G does not have a clique of size greater than V over 2. So previously what we saw is that G does have a clique. And now I'm giving you essentially what's called the complement language. G does not have a clique of size at least V over 2. Is this an NP or not? I want you to think a little bit about what does it mean for a certificate now? What does certificate really mean now? The certificate has to prove the non-existence of a clique. Right? And it's not obvious that such a certificate exists. Right. Okay, good. So how many such subsets are there? Right? So you get this, and this is exponential. This is exponential. I mean, this is basically like, I mean, it's 2 to the v divided by root v. It's theta of that. Okay, so it's exponential. So the obvious certificate is exponential. You could ask, is there a smaller certificate? Is there a smaller certificate? So the obvious certificate is all subsets of size greater than v over 2. But this has exponential size. Is there a small? This is a big open question. And we'll see this. This is actually an even harder problem than P versus NP. It is believed that the answer is no. It is believed to be no. We think no, but then, and this is called the NP versus co-NP problem, which I'll get to. But you can see that the obvious certificate here now has exponential size. What is interesting is that there is a certificate, there is a small certificate, there is a small certificate, or I should say a polynomial. By small I mean polynomial certificate of not being in the language. So if you wanted to certify that a graph is not in the language, then there's a polynomial size certificate that can be checked efficiently. And what is that certificate? exactly. It's just going to be the clique, exactly. Which is presumably what you admit, right? So the thing is, if it's not in the language, then you have a certificate. But if it's in the language, you don't. So note that there is an asymmetry here. And we will revisit this asymmetry shortly. So I want to say a few things and then, take a break and maybe answer more questions. So I want to state a theorem because it's not immediately, it's not hard to prove, but it's not immediately obvious. You need it's a useful exercise that P is a subset of NP. Now the question is, what is the certificate for a language L in P? Okay, let's go back to our definition. What is the certificate going to be? Right, so we said that if X is in the language, there should be a certificate such that MXY accepts in Qn time. And if X is not in the language, then for all certificates, MXY should reject. Now, if L was itself in P, was polynomially decidable, what is the certificate going to be? So let me give you a few choices. I want you to sort of answer this. This is somewhat of an ill-posed question. I want you to think about this, though, and then, I'll poll you. So what is a certificate? It's everything. The certificate is nothing. There is no certificate. Or C, it's whatever you want. So let me go ahead and, what is a certificate? Sorry, let me just start the poll and then I will answer that question. Maybe what I mean is that every string is a certificate. No string is a certificate. Or the certificate can be any subset of strings, we'll say any reasonable subset of strings that you want. You can choose what the certificates are going to be. Somewhat of an ill-posed question, and maybe your answer might differ from mine, but then I just want you to think about what is a certificate going to be. It's likely that this is not a perfectly formed question, but I want you to think about what this means. I guess what I mean to say is that, can you design a verifier where the certificates are, let's say, some subset of your choice? So more clearly, so what is the verifier going to do? The verifier, first it just runs, I'll say, suppose L is in P, decided by a polytime Turing machine M prime. So the verifier just runs M prime of X. Okay, so if X is not in L, then just reject. Then what I can say is, if Y is a certificate of my choice, accept, else reject. And I'm assuming that there exists some certificate of my choice, that the certificates are some non-zero subset that I can select from. I sort of put this only to say that, you might think that I can just say if x is not equal to L, reject, otherwise accept, which works as a verifier. You can also put in this extra condition just to say specifically accept some certificates over the other. Does this make sense? Yeah, it's arbitrary. It's arbitrary. It's as long as it's decidable in polynomial time, right? So you need to have some polynomial time procedure here. So that's why I said it was ill-posed. But what I wanted to emphasize was that you can basically choose. You can say the certificate is going to be the all zero string, or the certificate is going to be the all one string. Or you could say, the certificate has to, represent a connected graph when interpreted in this way, like whatever you want, as long as this is decidable in polynomial time. So I'm going to pause here. I will take a bunch of questions, and then, then maybe I'll talk about a few more things towards the end. So now that we have the definitions of P in NP, I'm going to give you an exercise, and I'll sort of sketch out how you would prove this exercise. So let me first define a non-deterministic Turing machine. Basically has a non-deterministic transition function. So the transition function, remember that the transition function previously is like Q cross sigma, whatever sigma with this. And the non-deterministic Turing machine now basically has options. It can choose a state, a symbol to write, cross, left to right. Right? So it basically has options. It has a non-deterministic transition function. And we'll say the running time is an upper bound on all computational paths. So does that make sense? So I'll say that M runs in t of n time. What this means? This means is that for all x, such that x has length n, all computations of m of x, run. And this is sort of the cleanest way of defining what is running time for a non-deterministic Turing machine. So I'm not looking at only an accepting path or a reject. I'm just looking at all paths. This makes it much cleaner. And so just like I defined d time, I can define n time of t of n. So we say L is an n time t of n if just using the definition of P, or I'm sorry, using the definition of d time, if there exists a standard, what's called a non-deterministic Turing machine. So the n means non-deterministic Turing machine, and constant c, such that m decides L and runs in c times t of n time. Now I'm stating this actually as a theorem that NP is equal to the union of all natural numbers of n time n to the c. Note that I'm stating this as a theorem, not as a definition, Because I have defined NP according to verifiers, which is a different definition than this. The common definitions of NP are often this. You actually define NP to be this, and P uses D time, NP uses, and that's why it's NP, it's non-deterministic time. Although off late, many people in TCS have felt that this is actually not the best way of explaining it. It's better to explain it through verification, because the concept of verification in certificates is one that appears over and over again, through TCS. But both of these are equivalent perspectives, the perspective of non-determinism and the perspective of certificates. So this theorem needs a proof now. I will leave the proof as an exercise, but let's discuss it. Do you see how to prove the statement? And this maybe is getting towards the questions of what is the notion of a certificate. So how do you prove the statement? Right. So, and I guess you have to do it. You have to do it both ways, right? So you have to define the certificate for the non-deterministic Turing machine, so that this is a subset of this, and then you have to show that for any machine that behaves as a verifier, that can be simulated by a non-deterministic Turing machine. I'm actually going to maybe add this question to the list of homework problems. And I might update the list of homework problems, because I think this is an excellent exercise in getting more convenience and getting more fluent with the definition. But let's talk through how one would prove this. So sorry, let me just go ahead and start to initiate the discussion, right? So I'll just say proof sketch, right? So this is not a full proof. I'm just going to sort of sketch out a few ideas. So suppose L is an NP. So now you need to show there exists a constant C such that, my apologies, by the way, the C has been overloaded here. C has been overloaded here. So this is poor. This is poor writing on my part. So maybe I'll just make this constant alpha. Okay. C says that L is an n time of n to the C. Okay, this is what you need to show. How will you show this? Exactly. So what the non-determined, you could take this machine, and what it does is it simply, on the tape, writes down what y is non-deterministically. Right? So it non-deterministically writes out the y, and then just goes ahead and runs this machine. So it's interesting, right? The non-determinism is sort of like front-loaded. It does all of its non-determinism initially, and then it just goes ahead and runs deterministically. Right. So what you do is, essentially, you non-deterministically guess the certificate. Okay, and now suppose L is in n time n to the C for some natural number C. We need to show that L is an NP. How does one do that? Your certificate would be the accepting path, right? So essentially, you think of a Turing machine that essentially the y tells its y is the list of non-deterministic choices that need to be made. So the non-deterministic transition function has to make choices. This just tells it what those choices are. So the certificate is the non-deterministic choices that need to be made to accept. And then if you think about it, this is exactly the definition of non-determinism. Right? What does non-determinism mean? It means that there exists some non-deterministic choices to make it accept. And when it's not in the language for all non-deterministic choices, it rejects, right? That's what non-determinism means. And so from that perspective, you see the equivalence of non-determinism and the certificate language. The certificate, I should say, semantics. Right? So in this case, the certificate is the non-deterministic computational path. So I've sort of told you the basic ideas. I think it's a useful exercise for you just to write it out, and I will likely add this to the homework. And if I make edits, I will let you know. So let's end here, and I can take any questions at the end.